Hello, everyone. Can anyone hear me?
I can hear you.
You can hear me okay, Faye? Yeah. Okay. Hello, everyone. We're a little bit early, so we'll give it a few more minutes until our speaker joins us, and then I can begin. Um, but in the meantime, my name is Tommy. I'm going to be the moderator for the session. So if you have any questions, feel free to use the chat. I'll keep my eye on it. We'll take breaks during the session to address questions. And during the breaks, I think it would be a good moment uh, to also unmute yourself if you wanted to ask a question directly. That would be okay too. Um, but we'll get into all the details in a little bit. Hello, Shazab. Hello, Sad. So we have a few people from Pakistan. Hello, Alan. Welcome.
Hello. Welcome. Hey, how you doing? Can you hear me?
Yeah, yeah. Hi, Dr. Garcia. How are you?
Good, and you?
I'm doing well. I'm going to be filling in for Dr. Paley, and I'll help moderate and guide the discussion today.
Okay.
Maybe we'll just give it a few more minutes.
Sure. Let's make sure you can see my screen.
Okay. Um, I see the welcome page at the moment that RCC has up.
Mm-hmm.
I think yes. I think we're good. I think these are your slides, right?
Well, but can you see my screen?
No, we cannot see your screen at the moment. Maybe Faye, would you be able to? Yeah, I think.
Because I would like to use the ones that I have right now.
Right. Maybe if RCC stops sharing, then you can share your screen. Yeah. See if you can share your slides now.
Okay.
Yep.
Can you see?
Yep.
Okay.
And if you
can you see while I'm flipping? I just want to make sure.
Yep.
I'm flipping right now between different screens. Okay.
Yep. We see Eclipse and we see PowerPoint. Yeah. How's the weather in St. Louis? I'm in San Francisco right now.
Cloudy with been raining and cold and hot and cold and hot. Yesterday was 55. Today is 65 to 70. So it's like a roller coaster around here.
Yeah, it definitely swings.
It's a lot of swing.
Yeah, I used to live near Michigan, in Canada, actually. So I'm familiar with the weather swings.
Yeah.
Talking about. Definitely.
So are we gonna try to do both today?
Yeah, I think we were thinking of a 2-hour session,
okay.
And we'll take a break in the middle and just see if there are questions, and I think we can get through both of them. How does that sound to you?
Yeah, that's fine.
Awesome. Hello, everyone. Welcome to the session. We're going to begin shortly in a minute. Okay, when we get started, looks like we have 20 or so participants. That's a good group.
Okay.
So again, welcome to the 4th session of this IMRT curriculum. Today we have Jose Garcia-Ramirez, who will be talking to us about clinical commissioning of IMRT VMAT for volumetric standards MLC-based delivery systems. Before we begin, just a little bit about background for Dr. Ramirez here. So he finished his master's degree from Finch University in Chicago, and then he also completed his residency at the University of Chicago in 1997. He's been working with WashU in St. Louis since 2001, and in addition to IMRT commissioning duties, as for every certified medical physicist, he also does a lot of work with brachy and other radiopharmaceutical therapies. So I'll let him take it away, and
And if you guys have any questions, please feel free to post and we'll try and address them as we go along.
All right. Good afternoon or good morning, or I really don't know the time zones that well. So today I'm going to be talking about, and thank you for that introduction, by the way. Today I'm going to be talking about clinical commissioning of IMRT, either DMLC or VMAT, with MLC-based delivery systems. Again, this will be the goal of our lecture today, among others, and I'll be happy to try to answer any questions that you may have. And if I don't know the answers to them, I definitely have a whole lot of people around me that are better experts and some other subjects, and I will find the responses or the answers to whatever questions you may need. One thing to note is that I like 3-letter acronyms and use them a lot across my presentations and documents that I used. So I put out this sort of glossary of terms, but it's mostly of acronyms so that you know when I'm writing stuff in the slides, what I'm kind of referring to. And if you have any questions, again, about any, 3-letter word that you don't understand, just feel free to stop me and let me know, what does it mean? I need to disclose that this talk is oriented towards variant machines. It's the machines that I've worked with. I haven't had much with other pieces of equipment, but the concepts should be applicable across the board. Presentation and during the acceptance, I used a lot of files that were provided manufacturing, only files, but also documents, reference documents that they provided for me to follow or for us to follow, and to also use as reference to determine different parameters or to make testing of the different parameters. These are DICOM files here that are on this side of this slide. I have put all these documents into that share folder that RCC has. And then lastly, most of the we did from parents for other. So that's fine. Technique, static MLC or the step and shoot. Basically, you have a static gantry angle, and the leaves themselves move during beam hold, and then the leaves reach a certain position, then the beam is turned on, certain amount is exposed, then the leaves move to another position, beam is turned on, and then it's a cumulative effect. But it is it's called the SMLC because it's just step and shoot, step and shoot. In the DMLC, or dynamic leaf motion, also called a sliding window, it can be delivered at a static gantry angle, okay? And during that static gantry angle, the dose rate, the leaves are moving, the beam is on, so the dose rate is being modulated and the leaf speeds are being modulated. And I will show you later on several pictures how this is, but for the time being, that's the explanation. And then the VMAT, it's DMLC, but now what we're introducing is gantry rotation throughout the delivery. So again, now the third component that we're adding on this is the modulation of the gantry speed, and also how to modulate the dose rate and modulate the leaves. All these things working in concert to create the fluence patterns that were required or that we need. Again, for data acquisition, this will be touched up on later. I'm gonna try to cover that. But I generated this presentation under the assumption that we're kind of validating the data, but this is just a slide presenting the kind of data that one would need to commission or acquire specifically for IMRT. The first thing is the data required for modeling on the treatment planning systems. It's very dependent on the treatment planning system. So you're going to need to find out all of the condition that you want from the vendor of the treatment planning system and determine what are the requirements, what measurements do I need to make in order to be able to commission either DMLC or VMAT machine. Some of them should require, or most of them should require at least measuring very small fields, like a 2x2 field generated either by JAWS or generated by JAWS and MLCs. And you want to measure, of course, output factors, percent depth doses, either for JAWS or generated by MLCs. And if you want to test sort of what I call semi-extreme conditions, you can also generate big fields with big jaw fields with small little MLC fields to test the capability of the software to be able to account for the differentials in between phantom scatter and head scatter and MLC lead transmissions. For assessing the validity of the data in the treatment planning system, of course, one is to compare the output factors, and one is to compare the percent depth doses either against published data or mostly the manufacturer's supplied data to at least determine if the data that is in the treatment planning system is appropriate. In terms of the head scatter factor, again, these are all verification measurements, what we're going to be talking about here. The measurements may not be required for head scatter factor data, but if you're doing hand calculations, it will be good to make those measurements and have a perspective on what they are. And the document that I like to reference and follow, it's the task group from AAPM TG74, which guides you on how to make those measurements. When comparing or making measurements, one recommendation that they do is, of course, to use small ion chambers for output factor symmetry. Here at WashU, to use the measure our PDDs and measure our output factors, or CCO4 for regular and larger volume chambers. 4 to 6 millimeter diameter. This is a 2 to 3 millimeter diameter. This is about a 1 millimeter diameter. So I have the specs on the and in the other presentation. For profiles, we like to use diodes. Diodes when one is doing profiles in order to be able to map out the shoulder or the penumbra, both of JAWS and of the MLC, and characterize it in the best way. For IMRT specific data that needs to be acquired, it's one that it's used by the treatment pool to determine what are the dose in the low dose regions, but like fields of collimator, all that transmission dose should be characterized between the abutment region. Again, that's so that it's modeled appropriately in the treatment planning system. For DMLC gap or dynamic dosimetric leaf gap, that is basically the number of how much gap there actually is in between MLC the actual dosimetric leaf con what they change. And if that they need to be, this is kind of like generalized equipment to be utilized, what kind of phantoms you need, arrays, detectors, etc. Just to let you guys know. Again, pointing out in terms of data acquisition, what things one needs to look at. If you look at over here, and again, I'm going to briefly mention this. This is why they say pay attention to the use of detectors, and in particularly to try to use small detector as possible, because during those small field size measurements, there's a lot of variability in the measurements, and this variability is mostly related to the detector volume size, or the diameter that the detector is the measuring diameter or measuring distance that it has relative to the field. So you want to detect that it's really small. That way you don't average out over the field, especially if you have 1 centimeter distance or 1 centimeter square fields.
Jose, we had a question in the chat about detectors. Can we use data acquired with a diode in Eclipse? I don't know if you have experience with that. And maybe you can even talk a little bit about differences between photons and electrons. It might be more appropriate. But for commissioning, would you use diodes at all?
No, for percent depth doses, I would not. For profiles, yes, to compare against.
Yeah. Okay. Thank you.
Yeah, I think for percent depth doses, I will definitely use small field, small diameter ion chambers to get those small field profile measurements. But we'll talk about a little bit more on this subject on the next one. But I'll write down the question. Photons.
Yeah, I think there was the question was about diodes and Eclipse. Maybe they're one.
I think for the Eclipse treatment planning system, I would do ion chamber measurements with small field ion chamber. And then also, instead of using diodes, I like to use the micro diamond detector because it's more water equivalent and has less energy dependence than the diodes do. But again, since we're going to be comparing against Eclipse, and Eclipse should have its own gold beam data, I think it is suitable to be using a small field ion chamber. So for data acquisition, again, volume sizes may be an issue. And this is depicted by this plot over here, and we'll go over it again. The alignment of the detector relative to the beam scan direction. It's important as it is indicated here. This is sort of a image or a plot of basically trying to point out, hey, if you don't align this detector relative to the beam scanning axis, you're going to have issues in your measurements. And if you well, that's basically this plot. We'll talk about a little bit more later. One thing I'd like to mention though is to compare different detectors. Again, you mentioned whether the diodes or ion chambers, it would be prudent if you have them to actually compare the data that you might get from the two different ones, okay? You want to compare against these data with others and what others have measured for pieces of equipment that are similar to the ones that you have, and if there's any reference data to actually look at that too. So for us, or for me, these are kind of like my detectors of choice. You got your large volume ion chamber that has been calibrated with an observed dose to calibration factor. I got my diodes that are to be used for profile measurements. We have used this diode also for output measurements in the small field scenario and compare it against the small field ion chambers. But mostly, this is the one that has been for now setting up as our reference for our 1x1 PDDs and our 1x1 profile measurements and our one by ones output factor measurements. We like this micro diamond because it's the closest thing that has come to be with other detectors. We've also used this type of plastic water to make measurements in a phantom when we need to. We have used two-dimensional instrumentation like this matrix hardware that comes with a software for analyzing the acquired data. We have also used this software called a dose lab that can analyze DICOM information acquired from an EPID or a DICOM distribution that is exported from the treatment planning system, and has the different tools to evaluate and compare, and also do routine quality assurance on the unit. Right now, we're starting to use this utility a lot. For film dosimetry, I liked this software package called Film QA Pro for making my film measurement analysis. Again, the major reason is because they actually they not only give me the film, they tell me how to handle the film, they give me a procedure. It's a very sort of packaged film dosimetry software and hardware and instructions that I like. Film dosimetry is uncertain enough to, count them.
I haven't heard of Film QA Pro before. Is it open source or?
No, you have got, it's bought from Ashland. Ashland, I forgot the name of the company, but it's okay. Ashland.
Okay.
And I can give you the web address later on.
Sure. And I think a Dose Lab is with Varian, right?
Dose Lab used to be an independent software, but it got bought out by Varian. Yeah.
So neither of those softwares are free for our audience. They're part of.
Yes. Well, this Dose Lab might come in with part of the purchase of the linear accelerator. I don't know what kind of deals you may work in, but if you're in that process, you may want to get this software.
Right.
The Dose Lab, because the Dose Lab software will still work with this combination of film and this combination of scanner, which, by the way, they recommend this 10,000 XL bed scanner, but I found that this cheaper one works better. I mean, not better, but it still works, and it's cheaper.
Thank you.
Excuse me. So, and then the hardware and software come packaged with, their portal dosimetry hardware, and within their software, within the Varian software, they also have their portal dosimetry package. This needs to be characterized before, full-blown use of it, but it's pretty neat. Once any characterization, it's not that hard if you follow the manufacturer's instructions. And and we have compared this portal dosimetry software against film dosimetry performed this way or performed with the Dose Lab. And we're right now at a point where we're like, okay, we're just gonna do, especially for our routine patient QA, we just go with this. Now, for like an acceptance testing, then since we first did some measurements with this and then compare it against that, then once we got comfortable with this package of the film dosimetry and EPID, then we kept on doing measurements with this. You understand what I'm saying? It's a matter of cross-referencing or cross-checking with something that you know and understand with something that is kind of like a black box.
Yep, that makes a lot of sense.
So in that's sort of the basic principle with anything during the commissioning and acceptance procedures, is trying to look at what others are out there doing, how's it compare with ours, how's it compare when I do it this way or that way. I can tell you my recommendations, but you may not have the budget to be able to do it, and we can point out to the closest thing that will give you the closest value within a certain percentage that you're comfortable with. Oh, sorry. So this slide here, again, I'm talking about validating the data in all this process with this instrumentation that you see here. One thing that I didn't tell you is that this small volume chambers, especially this the 0.125 cc's, which we use a lot for our routine patient IMRT QA measurements, they don't usually come calibrated with an observed dose calibration factor. So you usually probably have this big, large chamber, but you need at least this one to be able to make some measurements in small fields. Now, the uncertainty is going to be greater depending on how small the field is, but it wouldn't hurt to have this type of chamber calibrated with an observed dose to water calibration factor. Now, that's expensive, so you can get this one, which is the standard chamber for calibrating your beam, and you can cross-calibrate the rest of your chambers. Okay, and this is why I put this slide here, which is a new slide that it's probably not in your documentation, but I will upload the data today. And it's just instructions on how to basically do this cross calibration before you set out to validate or make measurements either in water or in a phantom with these small chambers. And the basic procedure is you want to set up your large chamber in a certain geometry. Okay, I'll explain it here. In this case, in a water phantom, at 100 cm, a depth of 5 with a field of 10 by 10. You want to make sure that the ion chamber is stabilized or give some time so that it equilibrates the water. And then you just irradiate it with a certain number of monitor units. And then you take that chamber out, you put your small chamber in, and you wait again a little bit, you're radiated with the same number of monitor units, and then you just basically use the equation downstairs to estimate and calculate what the observed dose to water calibration factor would be for that small chamber. So the way that I did the validation of the data that was within my treatment planning systems using, in this particular case, you can use any of these, but I think I ended up using a CC04 chamber for this particular measurements. Again, I had an ADCL big chamber, but I determined an ADCL factor for my small CC04. I created a treatment planning in the treatment planning system here in Eclipse. You can create a water phantom, and then what I did was I set up at 100 cm SAD, so the chamber or the point of calculation was here. Depth of 10 centimeters, SSD of 90, as is stated here. In water, depth of 10, 50 cm of backscatter, and 100 monitor units per calculation or per field. So I did that. I calculated those doses for the 2, the 3, the 4, 5, etc. And this is what you're seeing here, the calculated doses from the treatment planning system for under these conditions, okay? And then all I did was just normalized that these calculated values, normalized them to the 10 by 10 field, all right? And this is the rate, that normalization basically is the calculated output factor that the treatment planning system is basically utilizing, or that it's seeing. And then I compared those calculated output factors with the measurements that I did that were under the same conditions. And I was looking for an agreement of less than 2%, and that's what I got. So I was happy with the calculated, or with the output factors that were already inputted into my treatment planning system, and make sure that at least my measurements were in accordance with what it was calculating. Now, I haven't touched on reference data, but we'll deal with that later on. Okay, this is how I validated what it was being seen, okay? Same thing with the percent depth dose. I calculated a PDD in water using a similar phantom as this setup. And then I calculated the doses, and then once I calculated the doses in the phantom, I basically used the tools provided by Eclipse, and I exported that PDD data into a program. Basically, what I use is Excel to export data. And after I export that data, I normalized it to 100, of course, at a depth of the max, and then I compared the data against, in this particular example, against the measured data that I acquired. And what you're seeing here is the measured and calculated, Eclipse calculated and measured. This is for a 6x 2x2. They're matching up pretty good. What you see are error bars that are in percent depth dose, or in this way, that are within 2%, and then this way, they're within 2 millimeters. So I want to see at least both lines within those bars, and that's what I was seeing. to characterize or kind of estimate the MLC penumbra based on the leaf sides or leaf ends. I usually use the EPIT in order to do this. It was simpler and faster for me. But again, you can use the film dosimetry software to be able to accomplish a similar thing. But if you're going to do the film dosimetry software, you're going to have to scan a phantom, import it into the treatment planning system, make sure you have a CT to electron density conversion, and that conversion is appropriate. And when you do film dosimetry, you got to pay attention to registration. With this, with the portal dosimetry package of the linear accelerator, things move much faster. All I did was created the field. I delivered the field on the portal dosimetry, and I intercompare with a use the software tools to intercompare, and they can calculate the gamma in order to determine if there is good dosimetry within a 2%, 2 millimeter criteria. And in this particular example, this was that 2x2 field, and most of the pixels are like 98% pass rates at the 2%, 2 millimeter criteria. So both in this profile and in this profile. So I was okay with that for me characterizing. Now, I will show you a different way to do it in the other presentation. So in order to validate another measurement that I did for validation purposes was, this was to validate both the absolute dose calibration. So the treatment planning system for each machine, you have to sort of specify what the absolute dose calibration is and what the absolute dose calibration conditions are, or the machine count or output. And just to make sure that in the treatment planning system that is placed. Okay. So to check that and to check also how the treatment planning system was handling collimator scatter factors, I scanned water phantom to put an ion chamber in, or you can do it also, do these calculations in a pure water phantom within the treatment planning system. So you can use this water phantom, or you can scan a phantom with an ion chamber, either or. And what you do is you set up your fields, as you can see here. I've set up different fields at particular depths, and this particular depth here, and it was 7 centimeter depth, 93 SSD, with a source to chamber distance of 100. And then for the different field and jaw configurations, and for a certain number of monitor units, I basically calculated the doses at this point location. Okay. And then I went in with my ion chamber, and I put the ion chamber under the same conditions, and I measured the actual doses for those delivered monitor units. And that's what you're seeing here. For example, for this field here, that is a 15 by 15 jaw with a 2x2 MLC, my measured dose in water, it was 76. My measured dose in plastic water was 74. And then I compared that against the different ways that the treatment planning system is calculating. So the treatment planning system has the AAA algorithm, and these are calculated doses in water. Okay, and here the measured value was 76, so that's not unreasonable. I used the AAA calculated doses, but instead of in a digital water phantom like this one, in the ion chamber water phantom like this one. And in this particular case, it was 75 versus 74. Okay, so that turned out to be good. And in this particular example, you have the Accuros algorithm calculating with homogeneity corrections. And for this, we calculated a dose of 76. And again, we're measuring 74. And that was within a 3% uncertainty. So given the uncertainty specifically in the phantom calculations, I was looking for an agreement of 3% or less for this particular testing methodology. So
on the previous slide, could you comment a little bit on the 3% agreement, and maybe that has to do with because it's a small field? Normally,
so there were different variables. Oh, sorry. I accepted the 3% uncertainty in this particular environment because there's a combination of effects. Number one, It was a small field. It was a 2x2 collimator. And I remember that the size of the chamber that I was using at this particular point was the 0.125 chamber, not the pinpoint. Okay, so that made me may throw off the measurement, at least in the order probably 1%. So you have a collimator that it's really open, so beam transmission comes into play, so beam transmission modeling. So given that, and also the fact that we were measuring in plastic, and if the CT to electron density curve was not perfect, it might throw another error in there. So because I was trying to validate sort of the combined effects of things, a 3% agreement to me seemed to be a very reasonable, especially in the heterogeneous scenario. So for this one, I look for more like a 2% because it's a digital water, digital phantom. So that one is tighter, you know, in terms of the calculations, especially when you don't have to deal with the heterogeneities like this in this scenario. Does that make sense?
Yep, that makes sense. And I just want to make sure everybody understands that the last two columns on the right, those are different dose calculating algorithms, right? The ACF.
Yes. Yeah. So this is AAA, and it's AAA calculated in this homogeneous phantom. Okay. This is AAA, and it's AAA calculated in this phantom, which actually, you know, it's using the CT to electron density conversion table. It's got the inaccuracies in that. And then in addition to that, it's got the inaccuracies of my measurements. And then this one is a AAA, the Accuros in this phantom. So they were calculated in different ways.
Yeah, thank you.
And I was comparing the ratios between the calculated and the measured. For IMRT, those symmetry aspects, this is sort of the way that I see characterization of things. One should start with the alignment. So the first part was sort of me validating that the dosimetry data and the leaf end penumbra and the leaf side penumbra, the output factors and the percentage doses, so that basic dosimetry data was okay for me to continue characterizing the system for IMRT delivery. And then these next steps most concentrate on the characterization of the system or the RTP and the unit as a system. The first thing was the MLC alignment. Okay, light versus radiation, field alignment needs to be good, and also the light versus the MLC depicted radiation field also needs to be aligned. So that's one of the things you want to look at. And this is something that you do on an annual basis. So it's sort of part of the general QA that you do on the machine. Similar with the MU linearity, which is basically the dose per monitor unit, the amount of dose that you deliver per degree. This has to do with arc therapy, and it's gonna have an impact in the VMAT or the dose per degree. We characterize also the dose rate linearity, or basically the dose per MU to be independent of the MU per minute, or the dose rate at which one it's giving it. Again, the transmissions we talked about, mostly the average transmission is, at least for Eclipse, is the most important parameter to characterize in order to be able for DMLC and VMAT to be characterized appropriately. Then when you get into the SMLC, you want to make sure leaf positional accuracy is good. And also not only that it's good, but it's good at different Ganti angles. That way you kind of characterize the effects of gravity on the MLC movements and on the MLC positions. You also want to characterize the leaf, the penumbra on the leaf ends appropriately with scans or film dosimetry. That's another thing that we want to look at. For DMLC, we want to do all this kind of characterization and testing, but also we want to look at that dosimetric leaf gap, okay? In particularly because we're delivering this with a sort of a sliding window that is coming in and out instead of a segment and SMLC. So we want to characterize what is the actual dosimetric distance in between those two end leaves, because it's not the physical, and it depends on the MLC system that you have. We want to characterize how leaf speed and dose rate control are varied. And then for the VMAT, again, you want to characterize these, plus you want to add up the gantry speed and dose rate modulation, leaf speed modulation during rotational delivery. So sort of combination of things and things we need to look at. And we'll touch each one. So for the MLC alignment, I can't see, oh, there it is. MLC alignment to central axis. So this basic test just tests the offset and skew, and you can find this test in paper or a chapter by Lasasso, but it's basically 2 irradiations, and what you want to see is to make sure that your leaf or banks are aligned to the crosshairs, okay, as good as possible. Here in this image, you can see that because this and these are different, and this are different, it's a skew and a misalignment. And because of this, if this band is over here, then it's a misalignment. But when you have a band that is straight down the central axis and another band that is straight down the central axis, that's what we call a good alignment. So you can do this with film, you can do this with the EPID. Here I have demonstrated, or I have an EPID image of the crosshairs down my bands. You can see it here and here to the center to test that the MLC is not only aligned, but there's no skewness to the MLC relative to the central axis. And when I look at the profiles through it, what I'm looking for is that the peaks between the calculated and the measured are within the same, are basically congruent. And that's what you're seeing down here. Characterizing the dose linearity or the dose per monitor unit. I usually do this on an annual basis, or everybody should do it on an annual basis. You know, this tests that the dose per MU is independent of the total MUs. Okay, so where you give, what you want to do is you want to measure in plastic water. I usually do it with an ion chamber, a 10 by 10 field. I place the chamber at 100 cm, about 5 centimeter depth. Use a standard dose rate. So the test basically, it's a relative test that you should normalize to your standard dose rate. Okay, and we changed the MUs, but we delivered these MUs at a consistent dose rate or MU rate. So in this particular case, our selected dose rate, it was 600 monitor units per minute. So we delivered 2 MUs, 5, 10, 400, and 600. And then ultimately we compute the ratio of the mean divided by 100 and make sure that that ratio stays consistent and it's linear, okay? This also tells us when that amount of dose per monitor unit is non-linear. And this is also the reason why when we look at, in particularly SMLC treatments, the fields that have less than 5 monitor units per segment, we try to either, actually we use 4, because up to 5, our systems are still good, as you can see here. But below that, we try not to use, especially when we deliver SMLC, not to use lower monitor units, because the linearity gets lost. You don't have a linearity of dose per monitor unit, okay? Here we look for 3% variations or 2 MU discrepancies. In terms of dose rate linearity, you might want to make sure that the idea is to make sure that 2 MUs of those are 2 MUs, no matter if it's delivered at a 50 MU per minute or at 1,000 MU per minute. And this, to me, the machine was all the time that I testing okay, and I was like, okay, should we test this on a yearly basis or should we not? Well, guess what? We were doing a TBI treatment and we were finding some dosimetry issues with the measurements, and sure enough, we went back and checked, and there was a discrepancy in the linearity. So yes, it is an important thing to test on a yearly basis. It's relevant for static MLC. And again, on plastic water on 100 cm, I use a nominal dose rate for normalization. Okay, And well, this is an old plot, but our old dose rate, standard dose rate was 400. Now we switched it to 600, but the principle is the same. It's just to make sure that no matter at what rate you're delivering the monitor units, the dose is the same. If you deliver 100 at 600 and 50 and 100 at 50 MU per minute, the reading should be the same, okay? Or the dose should be the same.
Yeah, that's very interesting that you also mentioned the TBI treatment, because those treatments are usually at a lower dose rate, right?
Yeah.
So
that's where we found it. It's just not pinning out. So we need to figure out, and sure enough, when we went back, it was off by 2%, 3%. So that's what we're seeing, that 2% on certain beams.
And like 10 FFF beams can go to 2400 MU per minute. So do you also check for dose rates at those high levels?
Yes.
Well?
Yeah.
For FFF beams? Yeah.
Yes, we do it for the FFF machines. That is correct. All right. In terms of the transmission of the MLC, you got two major ones: abutment and interleaf. This measurement, you can do it with an ion chamber. You can do it in film or EPID. In this particular scenario here, I've used my EPID system to make my measurements. This is what we do on an annual basis. We take an open field sort of exposure or dose measurement or film measurement, and then we take a closed exposure film measurement. Again, when you do this, you want to have, because these are closed and you want to get a reading here, you have to scale up the monitor units in order to be able to get some transmission dose that it's measurable and not too noisy for you to say, to quantify it appropriately. So we deliver with the EPID, we deliver 50 MUs on an open field, and then we deliver 500 MU on a closed field. Then we look at the readings in this area for the abutment, then we look at the readings on this area, and that's what we utilize to make sure that we're within the tolerances specified either by TG50 or mostly by the manufacturer. And what I'm looking for is, interleaf, it better be less than 5%. And that should be for any machine. And the reason that is that, because, the whole point of having this kind of MLC system is to get away from blocks. And if we can't do any better than blocks, then the system may have an issue. And then for the abutment, there's some literature that states better be less than 50%, transmission especially through the rounded leaf ends. Our tolerances for our machines is 40% from the manufacturer. And this is, on an annual QA basis to make sure that the machine performance is appropriate. In terms of, this is in red here, just as an information, because whatever MU you choose for the open field, just 10 times that for the closed field. All right. Whatever, it doesn't matter what you're going to use, whether you use the ion chamber or film, but then you have to think about, depending on the detector that you're using, what is the resolution in terms of dose for that detector. I mean, film can saturate a certain amount of dose, so you got to keep that into consideration. MLC transmission measurements. Again, this is from the variant, the MLC procedure. Is to characterize basically the transmission measurement that is going to be placed actually into the variant treatment planning system. We do it for all energies. Usually it involves the exposure of an open field, and then you move the banks to one side and expose it again to another field, moves the banks to another side, and expose it again to another field, and then you can calculate the percent transmission, which is basically the average in between the two, and you ratio it out to the open, and that gives you the percent transmission that you can utilize. I've measured it in water, I measured it in plastic water with this, and they are very similar. So I've measured it with small chamber. This is a 0.6 cc's. I measured it at 0.125. It isn't that much different either. At least that's been my experience. And you can, if you want to really characterize you know, the average transmission through each of the leaves. You can, of course, like, I think this plot is from Easel. It's an old Millennium 404 MLC system, but you can see that it's about 1.5% transmission through the leaves based on this film dosimeter. So between 1 and 2% is what you should be expecting. The same document that describes where the MLC transmissions are made also describes the DMLC procedure. And again, it's needed for the RTP, and the way that the system characterized its or the procedure is you determine first that transmission, and this is where these measurements are from. The first set of measurements is the transmission set of measurements, and then you expose you take different readings for differing dosimetric leaf gaps as they're walking through the chamber. So this would be like a 2 millimeter dosimetric leaf gap here that is just starting here, and then it ends up on the other side, and it's just moving along in a uniform way. And I'll show you, see if I can, oh, that one I don't have. I'll show you the other one, but it's just a gap. This gap is just walking through in a uniform way to the other side. I have sent the DICOM files for it if you are interested in looking at it. It depends on the energy. You should measure it for each energy. Okay, it's in the order of 1 to 2 millimeters. Again, I did it in plastic water or same conditions as I measured with the DLG. It usually involves 13 segments. Okay, from here to here, from -6 to +6, they have 1 centimeter spacing. They all have equal mu per field. So it's a constant uniform speed. And you do this for bands of 2 millimeter separation, 4 millimeter separation, 6 millimeter separation, all the way up to 20 millimeters. And once you get all these readings, you plot them out in terms of the gap that you had versus the reading or the corrected reading. It's corrected for the removal of transmission issues following these equations. And then the projection back will give you your DLG that you should be placing in your treatment planning system, like here's 1.68. And also it will give you the transmission that you should be putting in your treatment planning systems.
Do you do it at different gantry angles or just 0?
No, I just do it at 0. I mean, yeah, I have done it at 0. I've never characterized it at different gantry angles. That's a good question, actually. But then again, that can be, any major issues will be seen with the ARC QA, and we'll go through that. So this is a static picket fence test that has basically the MLC positional accuracy. This test to me just looks, you can look at it 2 ways, absolutely and relative. So most of the softwares out there that analyze this picket fence, which is basically 10 segments, 1 millimeter slit, same MU per segment, which is usually 100. And you deliver this pick slits that are 15 millimeters apart, as you can see here, okay, or here, all right. You deliver them, and then what you're looking for is the relative separation in between the peaks, which should be 15 millimeters, and that's why most of the analyzing software looks at. It's just to make sure that all the peaks are straight, or the bands are really straight, and then the separation in between the bands, it's appropriate. So that tells me that the relative accuracy of position is correct, but it does not really tell me that the absolute position is correct. So for that, what I end up doing is kind of measuring the distance between where the gap is versus where it should be, okay? In this case, let me go back. The distance between here and here, I measure it to be 1.54 here. So it should be 15. So I'm within 0.5 millimeter. Okay, so that's in an absolute way. So absolutely speaking, at least the bands are getting positioned, the positions that I'm expecting them relative to central axis. So that's good. And then when I run it through the software, it's telling me that the straightness of all the leaves is great, and then the separation and positioning also the leaves are moving is great for all positional accuracy. Okay. I do the same test at different gantry angles, and this is basically the picket fence taken at the 0 gantry angle and the picket fence taken at the 90-degree angle. And then what I did is I could have used the portal dosimetry software, but I chose to use another software because at that time I was also comparing whether the portal dosimetry software was working correctly or was good. So in this case, what I use for comparisons, these are the portal images. I just exported the DICOM information. In this case, it was not to dose lab. It's the matrix evolution from IBA. The two-dimensional dose array has had the capabilities to read DICOM files. So I exported the DICOM files to that, and then I was just intercomparing the peaks over here, and just to make sure that the peaks were lined up between 0 gantry and 90-degree gantry. In order to see if my system can determine positional errors, the company Variant gives you a file that has introduced already a sort of an error in it, which is just a separation that it's different and is different from the rest by about 0.5 millimeter or more. And you can run that through either expose it in a film or expose it in the EPID to make sure that your system can pick up these issues with leaf positions or motors. For arc therapy, one needs to measure the dose, the DMLC dose versus gantry angle. So we start with a 4x10 DMLC field. It's a 0.5 cm beam slit, and it's got 300 MU per field. We're using a dose rate of about 600 monitor units, and we expose this over this band. It's 4 segments per field, and it's uniform motion. And we want to measure the dose or the counts in this region, sort of average it out, and compare in between the 0 exposure and the 90 and the 270 and the 180. And this is what this calculation is doing here. And this calculation sheet is provided by Variant, and all you're basically doing is comparing the counts or the mean counts here versus the others and the average. And again, I did it with the matrix software to make sure that the differences, the mean differences were, this was a 3% comparison. So I think for this one, I was okay. And then for this one, within 2%, I was okay. So the goal is that the dose is consistent and independent of angle during the DMLC delivery. To evaluate how that picket fence or how the DMLC delivery it's happening, we also want to do it during gantry rotation or an arc. So this is what we call the arc picket fence. And for this, you really need if you're doing film, you need a twicely exposed film to make sure that to be able to see the effects between non or static delivery versus rotational delivery. Again, if you're doing the EPID, I can capture one with a static delivery picket fence, then I capture another one with the rotational ones, and I wanted to make sure that the peaks, that the peaks again here are all lined up, which tells me that it's appropriate. If I'm using a software like DoseLab, was looking for doses between 3% and 0.5 millimeter in the peaks, just to make sure that those peaks align. After I'm done with that one, which is basically making sure that the delivery of the DMLC during rotation has good positional accuracy, I want to see how the control of the leaves and dose rate is. Again, Variant gives you this calculation sheet to be able to determine if your tests appropriate. I like to use the matrix software to be able to analyze that. This were captured with the EPID. And again, it's you can use film or EPID, but it's a 12 by 20 field size that starts at -6 and ends up at +6. It's 4 bands, as you can see here. They're about 3 centimeters wide. And then the dose per month, the dose or the MU per band is the same. So this is the same as that, as that, as that. And it should be the same as this homogeneous field that they give you. And then when you measure it and you ratio them out, you can see that the dose being delivered by the DMLC here and here and here is the same as that as the flat field. And you can see that by the white bands here. So I've compared them, and that's what you're looking for. Is just making sure that the dose, you analyze the regions in this area. It should be, the values on each segment should be equal, and especially when you're comparing it to the homogeneous value in that same section of the film. And that's what you're seeing here. I like this plot better because I can see as I plot one and the other one on top of each other, the bands should line up on the homogeneous field. And that tells me that the dose is, and leaf speed and dose rate control are appropriate. And this is sort of the field itself. This is a field with a treatment planning system. And I can show you at the end. I actually had it, but I think I'm running late if I want to give the other one. So you can see the different, how the fields are set up in the treatment planning system, how much gantry speed is required for each of the segments, and what the dose rate is, and how it's being manipulated to force those leaves to move at different speeds. To test the dose rate and gantry speed, during rotation, again, film or EPID can be used. This again, it's a calculation sheet that Variant provides you, where it tells you measure, after you deliver the field, measure the mean doses or the mean counts in these regions here, and then make sure that all those counts are the same basically when compared to what the reference field should be. Again, in a similar manner as the previous test, what I was looking is for those bands. Not the peaks, but the band mean doses, this mean dose here to be the same as the mean dose there. That way I know the control of the dose rate and the gantry speed is appropriate. Okay, now one personal note that I have on this test is that I'm really not convinced if this actually tests the delivery, the gantry speed. And the reason that I'm not sure that it tests the gantry speed in the delivery is because this test, even for the test recommended by the literature and the test from Variant, they use flat dosimetry relative to the beam axis. So you can test the dose rate, right, as you're rotating, and the leaf speed to make sure that the doses are being delivered on those bands are appropriate, or telling me that the dose rate control and MLC speed control is okay. But it really does not tell me anything because it's the same plane in terms of the gantry angle. I mean, I could deliver this thing static and I would not notice any difference. So to me, ultimately, delivering IMRT QA, patient-specific QA, is the ultimate test to me of that the gantry is being, it's modulating the gantry speed appropriately when we actually deliver an IMRT plan on a phantom. Does that make sense?
Yeah, that makes sense.
Okay. This is, again, this is sort of the end result. This is the file that I use to deliver into the EPID or deliver into the field, where it depicts again the different gantry speeds that the software is utilizing along with the MU rate. Now, all these files that you're seeing here, that's the stuff that I've already uploaded into the cloud for you guys to have, especially all these files here. See, what we're talking about thus far right now is the delivery and evaluation of all this arc rotation quality assurance, and acceptance testing file, from the dosimetry to the lead speed and dose rate manipulations. All right, so questions thus far, because I'm almost at the end, and I'm gonna jump through different.
Yeah, this has been great. There was one question when you were talking about linearity, and you know, we're talking about commissioning here, but when you're doing acceptance testing, is linearity something that is discussed with the manufacturer?
When I'm that first part of linearity, that's a linear accelerator related. I mean, it will be DMAT related too, because if you need it for it to modulate the dose rate, and you need to make sure that dose is linear, especially when the dose rate drops, right? That's what you're talking about. So, I mean, I expect you're asking me if I talk to the manufacturer about it.
Do you talk to the manufacturer, because it is LINAC based? So if you're just looking.
If there's a problem.
Yeah, like if you find, you said you go down to maybe 5 MU. For linearity. So if you find that at 10 MU, it's not very linear, would you bring that up?
Most definitely. Yes, most definitely. We have to figure something out. Most of the linear accelerators, things below 5 MU, I say below 4 MUs is when things start to drift. And you can see that in this plot here, right here. So you can see at 5 MU, and I don't even know, this is a 1997 paper from UK. So the gun controls in the linear accelerators, magnet controls, you know, all those systems are functioning. The pulse generation controls, all those systems are functioning appropriately, so that, you know, when you deliver a dose for 4 monitor units, you see 4 monitor units. Okay, so the dose per MU stays consistent. All right, no matter what number of monitor units you deliver. Okay, so that ratio of the dose per MU needs to be consistent. All right, does that make sense? And when it hits 10, it's less than 2%. Okay, at 5, it's still less than 2%. Okay, at 4, now the dose per MU drifts too much. Okay, so it's non-linear, so it's not what we're expecting.
Yeah, thank you.
And then I will address it with the manufacturer. It has nothing to do with the VMAT or anything like that. This is just a LINAC thing. That's why it's sort of at the core. All these things need to be functioning properly for the rest to be okay too. Especially in this case for the segmented MLC. All right, so sorry, I'm gonna fly through this. This slide is just a goal slice. When you're testing the system, the treatment planning system or the unit, you want to start with simple stuff in terms of patterns or things that you understand in terms of intensity distributions, and then get creative and complex as you understand and measure each and make sure it makes sense of the measurements. That's all this slides it's meant to convey. Okay, these are patterns created by people from Mayo, in which, you know, they started simple with simple patterns in a phantom with film, you know, and just scan it and make sure the calculated and the measured doses are appropriate. This cannot be done. This wasn't done with EPIT, okay? But you can, I have not created this pattern yet in EPIT, but I will. We've created others that you will see. Again, to test the system in a simple environment, to see the DMLC control, lead speed and dose rate, you can have varying dose or total MUs and dose rate over a field width, or keep the field size constant. You vary dose variables, you know, and you can modulate leaf speed and you can modulate dose rate to make sure you create sort of a homogeneous dose across, or create certain bands, and then you can measure the delivery and then see how uniform it is all across. In this particular example, we have the delivery to be within plus or minus 5%. based on this film. And what you want to do is tweak the transmissions and tweak the leaf gap to make sure that if you're trying to deliver a uniform film, you get a uniform film. Okay. Again, more creative patterns from Mayo. All these patterns are actually from a guy named, from a gentleman named Easel, and he is one of the main authors in a lot of the VMAT, DMLC, and MLC delivery, acceptance testing and commissioning. Different patterns that you can do and test, both test with film and ion chamber, and compare against the calculated values. That's all it is. It can be in a film phantom like this one. This is my film phantom, that I use, and this is my ion chamber phantom for my ion chamber measurements. But again, it's just a matter of comparing profiles. Now, this one I want to discuss because, you know, these are simple patterns. That is simple. That is simple. You know, these are simple things that one can understand. This one, to me, it's the paper that provides the, to me, the at least information on the variety of patterns that one can deliver to see what things are being tested in the system. So this pattern published in this Vonage paper, it was programmed mathematically, but basically what you're trying to deliver is deliver a homogeneous dose throughout the chair. And then because there are different sections, you're varying the leaf speed, and you can also monitor the transmission. So the idea is on this pattern here to deliver a homogeneous dose. Leaves are moving from here to here as depicted in this paragraph, depicted in this figure here. And this type of pattern, what it's trying to do is testing a lot of things. It tests the leaf end modeling, it tests the leaf side modeling, it tests transmission modeling, leaf speed control because things are varying, and dose rate control. So, you know, when we look at it, we look at sections in this delivery in this section here, which is basically through A, through here. And this area here kind of lets you know how much transmission is messing up. Looking at this area here, you kind of see if your leaf end modeling is appropriate. If you put an ion chamber here in the center of the field, which is here, you're going to monitor what the absolute dose is doing. So it's a really nice way that we use right now, and actually we use it clinically. We let me see. Sorry, I thought it was loaded up. But I have the pattern. I have not been able to extract it. And in all honesty, it was a mathematically created pattern. I have to consult with the gentleman that created it in our treatment planning system. But maybe Variant has a DICOM file that pertains to it. I was not involved in the import of this particular one. But for the other ones, like here's my Eclipse Phantoms that I just showed you. And for my Rapid Arc QA, you know, here's the first one that we talked about, the dosimetry at the different gantry angles. And you can see what the pattern looks like. So if we play it, oops. So see how that pattern is? So it creates this band, and it has these segments, and it delivers uniformly. Okay, so this is the file that I use for that first test. These. So here's the chair. So we have files, and we can use the portal dosimetry software to kind of compare and look at the different areas. And then we could probably modify our transmission and DLG parameters in the treatment planning system to best model this kind of evaluation. Task group 119 also explains or gives you the tools to be able to sort of test the system with examples on how to, it gives you specific instruction, it gives you data sets on how to make measurements and how to compare the data that you've measured with what they're expecting. These are sort of standard suite of test cases. Last thing is, when you are starting in your clinic, you know, you want to test the system at least to the extent that you have capabilities. In terms of the dose ranges from 200 to SBRT ranges, in terms of dose rates from 400 to 1400, try to make as many methods, as many multiple measuring methods as possible. You want to pick as many clinical cases that you might treat as possible in order to assess the full range of capability throughout the full range of clinical cases. Somebody asked me to explain this, and I don't think it's quite see, but so when I at my clinic, I was not doing VMAT, and I was not because I was using Pinnacle instead of Eclipse, and then I transitioned to Eclipse. But the data that was modeled in the system was GoBeam data, so that's why I did all this testing, is to make sure that the GoBeam data that was within the RTP system was okay for my machine. And it turned out, you know, you saw it here, it turned out to be okay. In the end, they were looking at the DLG, and I made the measurements of DLG, and it was not what they had. So we tweaked that, and then we started doing portal dosimetry or film dosimetry can be done, or patient-specific QA, to see if this transmission and DLG parameters were. And I did both measurements because I wasn't totally fully comfortable with the portal dosimetry software back then, but others were. And I did my metric measurements, and I did my portal measurements, and I did measurements pre-adjusting the parameters, and post-adjusting the parameters. And although here you can see that at least transmission-wise, things got better from this end. This is discrepancies high. This is the discrepancies lower. With the portal, I was able to see it much better. And the portal definitely told me that it was more sensitive to catch issues with the portal in terms of the DLG and the transmission than it was with a two-dimensional matrix system. Okay, you kind of see it, but it's not as clear. Okay, so that's what pre and post is. Pre, I adjusted the DLG and the transmission, and post, I adjusted it. And then in terms of the clinical cases, for example, here, what I'm showing is, you know, I did these couple of cases in terms of the dose per fraction, what the monitor units were. So these are the ratios between the ion chamber measurements that I made, okay? Then I made some film dosimetry using the Film QA Pro software. Then I made matrix for the same field to make sure that the matrix and the film were okay. Then I used a portal to do the same thing to make sure that all the fields were being intercompared appropriately. Then I used another part of the software that it's, this is basically a fluence comparison, and we use it for our routine patient QA. There's no calculations in this. This is just a Dynalog compare. So to me, this is the least thing that I think about. I was more concentrating on this, and on this to tell me, okay, everything seems to be working right. And this is some of my comparisons of all the different data that I found. I found that everything was reasonable. So we released the unit for treatment. And I did not include it here, but if you have heterogeneous algorithms, you might want to consider irradiating a phantom from RPC or another place that can sort of monitor your dosimetry. And in summary, so you want to be aware about the number of monitor units per segment. Okay, so MU per segment, I'd say 5 here. It's more like 4 to make sure that you have that linearity. Positional accuracy, especially this says this says greater than, it should be less than. This is incorrect. Less than 2 cm wide. Dose rate independent if you stay above 5 mu per segment. And when you look at SMLC delivery, you're looking at MU ratios. Oh, I didn't explain what MU ratios are. MU ratios are the ratio between the total number of monitor units in the plan that it's required to deliver the certain amount of dose. And usually for static MLC deliveries, that MU ratio is between 1 and 3, maybe 4 tops. For DMLC delivery, it's more like 3 to 10, and it depends how modulated the fields are. So for DMLC delivery, very depending on positional accuracy, leaf speed control, dose rate, modeling of the DLG, and the transmission. You can put it here. And for VMAT, gantry speed, and depends also on all these other MLC issues. Okay.
What would be the MU ratios for the VMAT IMRT?
For VMAT IMRT, actually, it's still around the DMLC range. Actually, they're lower, a bit lower than the DMLC.
Yeah, we find that
A bit lower. I'd say more like the 4, 4 range stays around there, 4 or 5. I don't think I've seen it greater than 6.
Usually, if it's higher than 5, it's like it's an overmodulated plan, and IMRT QA fails sometimes with those. So
yeah,
it's a good point.
It is. We are actually pushing. So I tell you what. So we had a. Oh God, what's the name of this type of treatment? You know what lattice treatment is?
Yeah, it's like grid therapy, but the new version of it.
Well, I'm not too familiar with it, but we're delivering with VMAT, and I wasn't too familiar with it. And in that lattice environment, you can see 6s.
Yeah.
Because when I saw it, I was like, man, this is a bit high for VMAT delivery. But then when I looked at the target, I'm like, oh, okay.
That sounds good. Okay, that was a great presentation. Should we switch over to the next one?
Can I get a 5-minute break and then I come back?
Of course. Take as much time as you want. We'll be here.
But I'll stay online, and then I'm sorry I flew. I wanted to present all this stuff so that people see. So if anybody wants to see it, I have my ARIA here pulled up, and I can show them the fields. But all these fields that I've talked about today, they should be uploaded in this, and you should have copies of those DICOM files.
Yep.
Okay.
That sounds good. Yep. Please take a break, and I'll chat with everyone, and we'll continue.
I'll be back.
Sounds good.
All right.
So feel free to unmute yourself or post in the chat if you have any questions, or take a break yourself if you need to. We'll continue again in a couple of minutes. Yeah, so there's a question about the lattice environment. So lattice treatments are usually done for large targets, and large, like we're talking, like 10, 15 centimeters in diameter. And what they do is, instead of treating the entire target and covering it to say something like we normally do with 95% coverage, or trying to get dose over the entire large target, they instead just place like a grid of targets inside the larger target, and they call that a lattice, which previously has been shown to be beneficial for these large targets with grid therapy. So grid therapy is similar to that, but it didn't use IMRT or VMAT. plans. Another question on the chat is the criteria for IMRT pre-treatment QA plan on portal dosimetry. That's a good point. So, you know, a typical IMRT QA criteria is gamma of less than 90% with a gamma threshold of 3% and 3 millimeters. So if 90% of points fail that gamma threshold, then that will be considered a failed IMRT QA plan. But depending on what kind of treatment you're doing, so if you're doing maybe a larger dose per fraction, then 3 millimeters, 1% threshold is used. So you can go more strict. 1%, 1 millimeter is the strictest one I've used, that I've seen used. And so that's something there.
All right. Questions?
Yeah, there's so I was just looking through some of the questions, and one here is I think would be ideal for you. It's categorize the ion chambers according to beam modality, like photons or electrons. So are you more likely to use one type of chamber for electrons versus photons?
No, I personally like to stick to the ion chambers for all the measurements. It's the one that usually comes in with the water scanning systems. And when we measured the PDDs, we usually stick up. Let me go down to the other one.
Yeah, that sounds good. And
so hold on, let me load up the other presentation because it's there.
Yeah.
But yeah, for PDDs, we like to. You can measure it with the issue that I have with diodes for photons is its energy dependence. So that's why I like to compare it against what I would get with an ion chamber. But diodes tend to be smaller, which gives you better resolution. So that's why I like the diodes, especially the edge diode for the profile measurements and the PDD measurements. I stick with the ion chambers. It's pretty straightforward, and based on the task group reports, there's standard corrections that you can make for the cavity diameter to compensate for the effective point of measurements. So that's usually what I stick with. For surface doses, as you will see, if I can load up my other presentations, I'd like to stick with the small diodes. Can be useful in measuring the surface doses, to characterize that dose between the surface water and the Dmax area for both the electrons and photons. But for the photons, I like better the diamond detector because again, it's water equivalent and it's very small, so I can characterize that better. Sorry, I'm trying to go here and here. And the task group report 106 that I gave you in the literature, to me, it's a really nice task group report that goes over all these subjects and points you into the direction of, it doesn't tell you what to choose, but it gives you the variables. I'm telling you what I'm more partial to, just depending on the logistics that I have, the equipment that I have, and how I'm going to be comparing the data versus what others have and what the other dosimeters give me. So when one is uncertain on the value that one is getting, I usually compare values in between two different types of instrumentation to see what kind of an error I have in the parameter that I'm measuring, and see if I am comfortable enough, or at least to have it characterized to the point where to say, okay, this is as good as I can do, but I know the uncertainty in this is this much. So even if I have that much uncertainty, I know how much it is. And when I'm making my recommendations to anybody as to answering a question of how much dose do you think it is, I can give them some error bars, at least. So did that answer the question or no?
Yeah, I think that answers the question. I think in practice, you would use either like a semi-flex or a farmer chamber for
Mhm.
your measurements, and I think I think that answers the question.
Yeah, and semi-flex to standardly acquire data. And again, if you are if you want to use some other instrument to see if it gives you different results and how much different they are, you're more than welcome to do it. But we found good dosimetry. Uh, we don't do a lot of I haven't done a lot of surface dosimetry. It's mostly IMRT QAs, but in the acceptance process in the beginning, and I didn't do this, it was some other colleagues of mine, they were making measurements in the surface with the diode just to model that surface dose as good as they could. But there's still some error bars. They say, well, it's going to be within 10%. Uncertain really at the surface. So we know that. All right, so in this same subject, so this part of the lecture is going to be talking about some of the instrumentation and data acquisition and scanning guidelines. Again, I said before, oh, can I start the other part?
Yes, please. That would be
Okay.
great.
So again, this is again driven for Varian, and you can see Varian gives you, hey, you have to acquire or you have to measure output factors. They give you the different setup conditions in which you need to measure this quantity. They give you the fields that you need to measure it to. You start with a 3x3 or smaller and then go all the way up. They give you the depths of measurements at which you need to make those measurements. And so basically the manufacturer tells you, this is the data that I need in order for me to be able to model the beam. And then you can tweak on this data depending on the end results when you're actually doing your QA with either film or with the other absolute dosimeters. Excuse me. So the first thing that I did, or that we did, excuse me, is look at, this is what Varian gave us. And again, I've actually provided this data to you guys in those files. That tells me this is the data that is in the system. It's called the Varian Gold Beam data. And the reason that we chose to go with this data is because all our linear accelerators sort of use the same data for calculation. So we have so many that we need to do beam matching. And then to beam match, we're actually trying to make sure that all our linear accelerators are satisfying this data here that the manufacturer gave us. But others have measured it. And this is for output factors. Others have measured the data. This is a paper published by JACMP. And you can see for different true beams, linear accelerators that they have measured similar quantities. For example, this 3x3 here is about 0.87 on this linear accelerator, and then the Gold Beam data is about 0.87 too. So that's how I say, okay, it's this output factor of a 3x3 is about 0.87. So whatever detector I should be using, at least should be somewhere around there within a 2% or 3% error bars. That way I know I'm not that far off from what others might be doing. So I do my search in the literature and see what others are doing. This is what this slide is trying to present. Also, I do it for PDDs. This is the Varian data. I don't have data for another manufacturer or from another paper, but this is the Varian data for the PDD that they gave us at different depths. Okay, and then one thing that I did was, okay, how does this data for a 6 MB beam compares for an open field under a certain set of conditions and field size compares with, these are standard tables published by the British Journal of Radiology. I think Varian follows the British BJR 17 when they specified their beam energy. I was comparing it against the BJR 25, almost updated. And if you look at the 10x10 here, and you look at the PDD at 10 centimeter depth is about 67.5. So again, I went to the 10x10 here, and if I look, and if I look at the 10th here, it's about 67 over here. So I'm like, okay, this is it, the energy of the beam is a 6 MBB. Okay. Before beam scanning and acquiring data, it's important to have alignment, mechanically and radiation wise. So light versus radiation field alignment, it's important. How the collimator settings versus the light field, it's important. The distance indicators, it's important. And the field size specified a certain distance, it's important also. Most of the recommendations and task groups use a 2 millimeter uncertainty, or to be within 2 millimeters. For IMRT, if I can, I'll use the 1 millimeter guideline, because especially in the alignment process, because you know, when we do our final analysis, we're going to be looking at gammas and distance to agreements to be less than that. So if these things are off too much, then your data or your measurements down in the end are not going to be as good. You're going to have to increase your error bars to be more like 3% or 3 millimeters. Okay, there's a slew. Are we okay with this?
Yeah, this is
Thumbs up.
good. And you know, sometimes we use 1 millimeter for SBRT sort of treatments, but if this is IMRT VMAT, then I think we follow 2 millimeters as well.
Yes, that is correct. But like I said, you know, it's sort of what it's recommended by TG 142 on the non-SBRTs or SRS machines.
Yeah.
They use the 1 millimeter there. But if you can, and it's not too much work, because sometimes running after that millimeter can go around and around and around. Try to stick it, especially the crosshair alignments and the light versus radiation. Those are two that I would like to stick within the millimeter if I can, because it'll help down the end, especially when you do film dosimetry. All right. Or any kind of alignment dosimetry.
Definitely.
All right. Beam scanning, there's a whole lot of pieces of equipment out there. This is from PTW, this is from SNC, this is from IBA, and each one has its own hardware and software packages to be able to make your measurements or acquire your data. To me, the most important things are specified here. First, number one is fitting the budget that you have to be able to buy with, but you want to look at what the capabilities are for this software to be able to export data from the software after you have acquired it, to see how you can make comparisons outside of any software. So export capabilities to me and formats is important, especially that it exports formats that I can read, like in my XLS files or text files, and then it can communicate with the treatment planning system or export stuff to the treatment planning system. So that way you can move data from the scanning software to the treatment planning software. It should be easy to learn and operate, minimal amount of components, interconnection, it'll help out. Should have automating scanning range detection limits. That means that you know, the scanner software knows the limits on how to move in any of the axes. That way you don't crush the ion chambers or anything against the wall of the system. It should have both continuous and discrete. I think in the end, I like acquiring things more in the continuous way. We use a high dose rate to deliver things. So given even though you're acquiring data points, the speed at which the data point it's being acquired, it's in microseconds. So it's fast enough that if you have a high enough dose rate, you can still get good smooth data, even using continuous mode. Discrete mode. I like the discrete mode, not the continuous mode. The continuous mode tend to be more noisy in the data, because you're going to see more of the fluctuations in the readings as you're acquiring your data.
What is the difference between continuous and discrete?
So in the continuous mode, you're kind of mapping out currents, and in the discrete mode, you're actually collecting data at certain time points. So you take a reading at a certain time point, reading at another time point, reading at another time point. and that's sort of a discrete acquisition. Okay.
So it's measuring charge at each point rather than just looking at the current as it's moving.
That is correct. That is correct.
Interesting.
So if you look at a system that is just looking at current, any kind of variability in the pulse rate or ripples in the water or scan speed, it tends to be a little bit more noisy. So I think that the discrete mode tends to be a bit more cleaner, and you will see this. We will see this. You want to have the software that you can manipulate the scan speed, and this is going to be important, especially when you're taking down data at the edges of the edges of the light or the field, and of course ease of maintenance, things that can be kept up and that's not too expensive. In terms of the equipment and ion chambers for beam scanning, these are my preferred. Instrumentation, again, the micro diamond detector for fields that are 2 centimeters below. And when I mean small volume or small field ion chambers or detectors, you want to look at diameters that are in the order of 2 to 4, max for 2x2 and lower, volume sizes that are less than half a cc. So detectors of choices are the pinpoint, the micro D. This is the micro D from PTW, the edge detector from, I think this is SNC, and the CC04 from IBA. These are all really nice detectors to be able to measure 2x2 fields, which it's usually how low we go. We have actually gone all the way down to 1x1s, but when we do 1x1s, we stick with the micro diamond. It seems to be the smallest one. And you can see it here, 1x1s, 2x2s, 3x3s. You can use this for both photons and electrons. Okay. Excuse me. From 3x3 up, we use chambers that have a size of about 5 to 6 millimeters. This will be the CC13 here, the semi-flex, which is here. Okay, these ones have about 0.1 to 5 cc's, around that volume. That's what we use for our scanning, which is this is C13, and this one have about that same 0.1 to 5 volume. Okay. So why selecting a detector size and why it's important? Here's the effects on output factors. Again, these are the different output factors as measured with different detectors, and you can see these diodes over here. Excuse me, I'm providing data. There are in the 0.6% range, PTW 0.3. As you increase the volume of the chamber, okay, as you increase the volume of the chamber, the output that you're measuring for the small field becomes lower, okay? So you're underestimating the actual dose delivery of that field, and ultimately, if you use that, you're gonna be overdosing those fields. So that's the major thing that you have when you're looking at output factor measurements with chambers, and there's not 0.6 is around good value for small field 6 MB beam to kind of keep in your heads for all these detectors. So what we use in our clinic now, it's the diamond detector or the pinpoint chamber to be able to determine what that small 1x1 output factor is. Excuse me. And when you can see, when you go to a 2x2 field, the difference between this 0.3 cc chamber and the rest is not that big. All right, so the error becomes less. In terms of the profiles, again, you can see this is the profile with the diode. This is with the edge detector, and you can see that comparing an ion chamber, which is a semi-flex, you get a bigger volume, gives you a bigger penumbra. A smaller volume or smaller diameter gives you a sharper penumbra that is more comparable to what you will get with a film. When you're scanning, again, a big volume, you're going to average out a lot, so the actual peak dose that you're going to be seeing is actually smaller than what it really is. Again, the effects are, in the end, you might end up over treating a patient if you don't characterize those small fields correctly. In terms of the penumbra, you're going to get penumbra broadening. So this is a scan with of a 2x2 field with a pinpoint, which is the dotted line. You see small volume gives you a sharper penumbra, larger volume gives you a broader penumbra. And in terms of the scans and broader penumbra, what you're going to end up is probably over treating tissue. especially when you're trying to cover small areas. Beam scanning, coordinate system. Okay, so this is one of my pet peeves when I scan, is that it's really understand what the X and what the coordinates are on your scanning software in relationship to your water tank setup in relationship to your collimator settings. Okay, that's the most important thing, because sometimes they have their own way of specifying or terminology, the scanning software, and they say cross line, in line, and if you don't know which way your tank is aligned and what it's calling X and Y and what it's measuring, you say, was this in the Y jaw direction or was this in the X jaw direction? So to me, that is an important thing, is trying to make sure that you understand the relationship with your linear accelerator setup, your tank setup and coordinate system, and your scanning software interpretation of all these components. That way, if you need to make any adjustments, you know how to adjust on the Linux. This is just, basics of tank. You have your water tank, you have your scanning arm, you got your chamber holder. This is the leveling arm. Most of the scanners have a setup like this. There is a reference chamber that it's placed above and near the head of the linear accelerator around here. Okay. The major tank leveling base. So gross alignments will be with this kind of base. If you can, micro alignments will be done with this setup. So most of the times comes with something like that. Direction and hysteresis, at least upon the first time that you use the tank, you want to acquire scans. First for PDDs, my recommendation is to scan the PDDs from bottom to top. That way you eliminate any ripples that may be caused by dipping issues, especially when you're doing electron measurements, who tend to have a high surface dose and tend to be more sensitive to water ripple issues. So scanning from bottom to top sort of eliminates that kind of thing. But also you want to, at least the first time that you use the water scanning system, you want to first look at how much hysteresis there is in the system, both in the depth scanning and in the profile scanning. And you do that by just scanning one way, then scanning the other way, and making sure that both of them are aligned and that the hardware is not causing any issues when you look at a profile or a PDD and it gives you two different results. As far as, what is this? Oh, sorry. Alignment, the first thing that I do is make sure that the gantry, it's leveled. Then I would set up my tank crosshairs to the crosshairs of the gantry, make sure that this is 0. Then I'll fill it up with water, make sure, move my ion chamber in the X and Y direction. So after I'm aligned here, I would take the chamber and measure it this way and move it this way, move it that way. And when I'm looking at it, I move it this way, move it that way, make sure that that the center of the volume of the chamber, measuring volume, is just moving along those correct crosshairs. And once that's done, and again, I do this with the chamber deep in the water, not on the surface. I do it, and forgot to tell that, but I do it with the chamber inside the water. And I'm looking at the projection of the chamber shadow over in these crosshairs, just to make sure it's not drifting. It's not going from here to here or there, or from here to here or there. Okay. So what if I forget to level the gantry? You can expect, especially in small fields, you're gonna see these peak profiles sort of moving. See how this peak is moving as you're scanning with depth? That's one of the effects of not having that gantry angle aligned. And then you can have also that the profiles are kind of offset, as you can see here. Okay, this is for large field effects and for small field effects. All right, and then also the another effect is you can have profiles that not only are offset, but that it's matching on one side and not the other. That's another effect of not having the gantry angle level. So now the next step in scanning alignment is the arm leveling and the surfacing. So for that, I will move the chamber again in the X and Y. So that means this direction, and then in and out from this plane. And I will look at the chamber underneath, and I will look for a circle. Okay, a circle will tell me that the center of the chamber is perfectly at the water surface level. And as I move it, I don't want to see the chamber just move like this or move like that. I want to see that perfect circle all the time as I'm moving the crop, scanning that chamber in the water surface, in and out and left to right. Is that I'm monitoring from this perspective for the in and out, and then I'll go on the other side of the tank for the other perspective to move this way and that way, okay? So perfect circle all the time, or perfect chamber shape. So if I forget to do this kind of leveling to the water surface, you can expect this kind of effect in this particular here. You're gonna see certain amount of alignment on one side of the profiles, but you're gonna find a total misalignment profiles that may not, that's supposed to be flat, that are not flat, okay? So these are another examples of issues that you may encounter when you don't align your scanning arm or you don't surface your water properly. And in terms of the depth alignment, basically I look at the ion chamber and the crosshairs, and then I'll move that chamber up and down and make sure that that chamber is not moving this way or that way or this way or that way from the central axis. Okay, and it's kind of hard to estimate, but I try to at least make sure to estimate this amount. I kind of know that the chamber dimensions are about 4 millimeters in width, 4 to 5 millimeters in width. So I kind of use that as a guide as I'm seeing the chamber travel up and down across the crosshairs to see if it's going more than what I'm expecting that way or this way or that way. Now, there are some softwares that actually have these automatic tools that it's used to kind of make that alignment of the central axis. And what they do is the software scans at one depth, and then it scans in another depth, and then it does so both in this direction, and then it does so in this direction. Basically, it's just aligning the both dimensions of the field. And it does apply this alignment to kind of tell you, oh, this is the center of the scanning square that I'm scanning. And the one thing you need to make sure, okay, it's when the software does that, you need to go back into the room and make sure that that's within a millimeter of where you saw the crosshairs were at. Because if that's not, then there's an issue with either the crosshairs or the jaw alignment. Does that make sense? Or the light versus radiation alignment?
That makes sense.
Okay. Alignment of the tanks or the ion chamber to the central axis. The major problem is with the small fields. You're going to find that your percent depth doses are all out of whack. It's due to the central axis runoff, and again, it's more important with your PDD measurements. For surface dose measurements, again, I said that we like to use small diodes. Pinpoints, I think, are good. We like to use the PTW, but small diodes for surface dose measurements are appropriate, as depicted this figure from, this is actually from task group 106. Of it, that it's one of the things that I found interesting when looking at this task group is I used to measure my surface doses with Marcus type or parallel plate type chambers, and because that was recommended back then, you know, because the window is small, so that's what you're looking for, is a detector to be as small as possible in the depth direction. That way there's not a lot of perturbation. But apparently, based on this based on this paper, it looks like the Marcus chamber may be more over-responding for photon fields, most likely because of the backscatter of the chamber itself. So for electron fields, the parallel plate types are okay for measuring those surface doses and measuring PDD type of measurements. But for photon fields, I wouldn't. I would stick to diodes or stick to PTWs. Does that make sense?
Yep, that makes sense.
Right. So parallel plates, okay for electrons, PDDs, and surface dose measurements, but for photons, it doesn't seem to be working out so well. How much do I scan? Oh, sorry, scan length. Yeah. So in our scanning for commissioning, we would go about 10 centimeters. For annual QA, we go about 5 centimeters. Okay, so you want to scan a good amount either underneath the MLC if you set an MLC field or a jaw, enough that'll give you an idea of what the transmission is. We call the penumbra the area between the 80 and 20% in our definitions, but you can define it some other way as the 90-20. But that's how much additional scan we do for each of the fields. In terms of the scanning speed that we use, we like to keep it, if we're scanning from the 80 to 20, basically from here to here, we'd like to use less than half cm per second. If we're scanning from here to here or from here down up, you can increase your speed because the gradients and the intensities are not varying that much. So interpolation in terms of the acquired data doesn't become a problem. Here it does here. So, you know, higher speed may not be an issue. What you can find is if you are scanning at too high speeds, especially in the high dose gradient regions like this one here, you're gonna see choppy data, especially if you're doing discrete. So in order to be able to resolve this kind of issues, you can scan at max and min speeds and compare the profiles and see which ones give you the smallest penumbra or the smallest dimension of this 90 to 20 or 80 to 20. And that once you hit that speed, if you go anything below and it doesn't change, then that's your maximum speed that you should scan. And I think we found that half cm per second works out pretty good for all across. So that's usually what we kind of stick with. But for accepting data acquisitions, I will just try to do half or less and see what the difference is in this area. We saw this slide already as to the effects of the chamber volume and the effects that it has on the beam profiles and profile acquisition. I think ultimately, if you have any questions as to which detector it's best to use, the best detector for characterizing this type of data, it's a film. It's the one that has the highest resolution. So if you want to compare against anything, it would probably, and see what the nominal is, it will probably comparing against film dosimetry. But ultimately, in the end, we're going to be doing that. Excuse me a second. Sorry about that. So these are the effects on both scanning directions and the orientation of the chamber relative to the scanning axis and the impact that it has. We talked, I mentioned about acquisition mode, continuous versus discrete. The red here is a continuous mode acquisition. This paper is from Cruz, from radiation measurements, and you can see how noisy data is. See how noisy the data is when you get continuous mode versus a discrete mode of acquisition. It's less sort of interpolation or instantaneous data acquisition. It makes for less of noisy data. And because when you get noisy data like this, okay, the issue is that you're going to be tempted to use the software tools to kind of smooth this data out. And then when you start using the software tools to smooth the data out, then you question yourselves, like, is that interpolation that the software did in smoothing that data appropriate, that represents the actual gradient in the shoulder here of the field? So the less software manipulation you need to do, the less noisier data you get, the better you feel about the actual acquisition, that it represents truly what is happening. So if the data is too noisy, you may want to decrease the acquisition speed or increase the dose rate. That way you reduce the signal to noise ratio. If you have too choppy data, I would just start by decreasing the speed of acquisition to deal with these issues. Output factors. Again, these are my definitions of output factors, just to present it. Rules of thumb that I use, the ion chamber sensitive volume dimensions, or it should be 1/4 the minimum field size diameter or distance that you're going to be using. So for 1x1s to 5x5, I will use a micro D, pinpoint, and edge detectors to measure this. You can measure it in water, you can measure it in plastic water, but I would use water. For 3x3s to up, okay, CCO4s or CC13s or things in the order of 0.125 cc's of volume. It's what I would use then to measure the output factors for those. Now, notice that I've used the small chamber from the 1 to 5, and I used a bigger chamber from the 3 to 5. And the idea is I want to daisy chain. Small volume chambers are usually not that great to measure big field size. They tend to over respond. So what we do is we tie up, we kind of daisy chain the data. And for the small fields, we use this detector. For the large fields, we use this detectors. And then we kind of start from the 1x1 to the 10x10 and 15x15 here, and we daisy chain the readings. That way, the output factors that we end up with are basically output factors that are measured with a small volume, but that are related to the large volume ion chamber. And here are the daisy chain equations that we get, and it's usually just taking data with two detectors at a similar field size, okay, or a similar in the similar conditions. That way you can kind of correlate one to the other. So here the output factor for a 4x4, okay, would be the output factor for a 5x5 acquired with a CCO4 times the measurement of the output factor for a 4x4 acquired with the PTW but normalized to the 5x5. Okay, and I think I gave you this Excel sheet too, but it's something that you guys can create. Here are the conditions for the measurements and what instruments were used and what field size were used for normalization. For treatment planning system parameters, we measure it at 95 SSD, depth of 5, SAD of 100. We use give 200 MUs to reduce the signal to noise ratio. For hand calculations, you want to use the Dmax location to actually make this measurement. Although it's not recommended to acquire data for modeling there. That's if you're just doing the hand calculations, that's where I would probably do it, or correct it for the TMR, however you want to do it. This is sort of the big plot. So this, I prepared this data table for collecting the data. This is just the big data acquired. And you can see again how the I've kind of separated these output factors, daisy chain, and they kind of should follow if you look at the curve that they generate, it should not be choppy. There should not be abrupt. It should kind of follow a smooth pattern. Is that the best way to say it? They should be smooth. Continuous. Yes, a continuous smooth, a continuous smooth shape, curve. I guess. Yeah, curve. So these are my instrument readings with a small chamber for this different field size. Then for the big field size, I used the CCO4 chamber, and we can take the readings there. Then from the readings, I can sort of compute the output factor that it's normalized to a 10x10, as you can see here. All right, I did it both for the 10, for the PTW, and I did it for the CCO4. The CCO4 is sort of the standard chamber from 4x4, you know, large field dosimetry, not a lot of uncertainty there because of lateral electronic equilibrium. So becomes sort of the standards up to a 4x4. So the measured output factor here for a 5x5, I normalized it to, the measured output factor with the PTW, I normalized it to the 5x5, and then I calculated based on this equation what the output factor would be for the small detector, okay? And that sort of became my data. Now I'm comparing this measured data against the manufacturer or a nominal reference data set to make sure that everything is okay. Again, the measured output factors, how do I compare it? Not only against the nominal or manufacturer recommended data, okay, but I also compare it against the one that it's calculated. And I think we went over this already in the previous presentation. Remember, I created a phantom, I set up some fields, set up some conditions, and I calculated doses on a point, and then I did it for different fields, and I used that data to create my calculated, instead of nominal, which is here, which is the manufacturer's recommended, okay, I went and calculated it, at least for up to a 2x2, and compared it to make sure everything was okay. All right, so I compared not only against the measurements against the manufacturer suggested here, but I also compared it against the calculated on the treatment planning system. Okay. In terms of collimator scatter factors, task group 74 is a great task group. This is sort of the conditions of measurements that you would utilize. Source detector distance usually is about 100. It's in-ear measurements with columnar phantoms or mini phantoms. You want to build up enough that you have CPE, charge particle equilibrium, and you want enough buildup that it can remove any electron contamination that you may have coming out of the collimating system. And also you want to irradiate the entire detector plus cap or mini phantom. Always, you want to make sure that you're always irradiating the full phantom itself, because you're going to be referencing that to a reference field. Okay, in our case, our reference field is a 10 by 10. And then when you go smaller, you want to make sure you irradiate the whole thing, in order to make sure that you don't include any kind of phantom scatter effects on it, and also to keep within the homogeneous part of the field itself, with the intensity, or within that 80% where the intensity is sort of homogeneous, and not include the effects of the penumbra near the field edge. For small fields, the recommendations are for small fields of 1 by 1 to 10 by 10 to use brass caps. For large fields from 5 by 5 to 40 by 40, they can use water equivalent lucite caps. And the task group gives you a way to actually construct this particular caps, even though there's some companies that have already created some of these build-up caps for the measurements. I don't like this stand, because I'm not sure if that's going to introduce any scattering issues. So the task group, and I also recommend to use some sort of styrofoam height column to kind of make these measurements, if you're going to venture out to make the measurements to have for your handbook data. Again, I as a first exercise, I would do it during the acceptance of a unit, just to have an idea of those collimator scatter factors. I do not believe that treatment planning systems are requiring for us to do those collimator scatter factor measurements. But if you are doing hand calculations and using Kahn's method, you're going to need that data in order to be able to perform your hand calculations. So it's good to follow these instructions to kind of measure. And this gives you an idea on how to, what the diameters here, and particularly what the diameter of the cap be, what the height of the cap should be for the different conditions. And again, when you make your measurements like before, you want to daisy chain them. For percent depth doses, we talked about exporting the data. We talked about selecting the proper detector. We talked about, you know, the importance of scan leveling and chamber leveling. When you're scanning, after your scan, just make sure where your effective point of measurement is, because once you're scanning, you're probably going to use that data for calibration. So you want to make sure where your scanners, some scanners actually manipulate the scan automatically. Some others you need to apply the corrections. So understand when your scanner is saying, you know, the chamber is at 10 cm, is it the center of the chamber where you set up the water surface level, or is it the effective point of measurement? So that's the thing that you need to understand from the software. What is it doing? Also, when you're scanning PDDs, when you're scanning small fields, you know, your scanning chamber is going to be here, and you want to make sure that chamber is always encompassed by the field as you're scanning up and down, or scan left to right, or you know, in X or in Y. So there's a reference detector that we utilize to kind of normalize the data that is acquired by the scanning chamber. That it's also to factor out basically any kind of instantaneous pulse rate changes that may be detected, because since you're normalizing it at two different points that are apart, but in the same beam, you know, small fluctuations can be factored out and not built into the acquisition. All right. So it's very good to always have this detector, but it's not absolutely necessary. This detector here, the reference, it depends on the stability of your linear accelerator output, okay, and dose rate. If your dose rate fluctuations is high, you know, when you're delivering, you know, goes from 500 to 600, you know, and it's fluctuating like that while it's delivering the beam, and you don't have this detector to factor that change, those changes out, your data on the PDD is going to be bad. Okay. Here I compared my measured PDD against the standard PDD. This was from the gold beam data. This is what I measured from the water scan. Again, I exported this stuff to Excel, as you can see here, and I compared using my 2% error bars on the y-axis on the PDD, and both curves are, you know, falling within those error bars, plus or minus 2%. I went and calculated again the PDD, but I calculated it in the treatment planning system, as you can see here. All right, and then I exported that data into, again, my Excel sheet, and I now compared the calculated PDD in full water phantom versus the measured. This will be the measured data from the scanning software. This will be the calculated data from the treatment planning system, and apply the same methodology. This was for a 10 by 10 field. So not only the nominal data is correct, but the calculated data is correct. Similar with profiles, and again, particular attention should be paid to where those profiles are in the crosshair. The measurement conditions are here and what you need to scan, but again, that's manufacturer dependent. Most of the time is a nominal thing of 100 SSD, and then you scan, we usually do 2x2s, 3x3s, 4x4s, 5x5s, and then 10 or 7, 10, 15, 20. Here's a comparison of the profiles. So again, here on their side, you have your data that was provided by the manufacturer, that was captured with an IBA CC13 chamber. You don't see the data here because this one is for a 4x4. So the 4x4 probably starts down here. The 4540 data is here. But this was what I measured for the 4x4 for my scans. And then I exported the data from my scans into my Excel sheet here and here. And then I'm comparing the data. And here for this comparison, in this direction, I'm using 2%. And in this direction, I'm using 2 millimeters. And I'm just looking for the calculated data or the gold beam data, in this case, the red line, to be inside those 2%, 2 millimeter bars, either 2%, 2% over in this region, and 2 millimeters and 2% within this shoulder region, and then 2 millimeters within this region, and 2 millimeters or 2% within this region. Does that make sense?
Yeah, that makes sense.
All right. Again, this is the measured versus the nominal from variant. This is my measured versus the calculated from the treatment planning system. And I went again and did the same thing. I exported the calculated data from my treatment planning system and compared the 2% 2 millimeter criteria on my profiles. And this is just at one depth, one field size, but you can do this for many. Yeah. In terms of film dosimetry for comparisons, I think this is a whole different subject, but I'm going to try to sort of cover it here in a jiffy. I use the Film QA Pro software, uses EBT film. I use the 8,000 scanner. They recommend the 10,000. There's something important about this scanning software, and it's the use of a glass plate. It's just a basic, about a 1/4 inch thick glass plate that is just used to place on top of the film. And the reason to do this, and it's recommended by them in their instructions, they actually tell you, they actually manufacture the plate for you if you want it. You can call them up and say, hey, can you get me the glass plate? And they'll make it for you and they'll ship it to you. That's what I did. But it is to reduce any Newton rings or anything, any variability during the scanning. You want to have that film as flat as you can for scanning, and it reduces some of these scanning artifacts out of it. So for film dosimetry comparisons, I had to scan a phantom. We usually use the plastic water phantom. You see the scanning by itself or with an ion chamber in it. I usually have about 14 centimeters. So I have 7 centimeters this way, 7 centimeters that way. In the one with the chamber, I use it for, of course, ion chamber measurements. The treatment plans after they're done are placed on this phantom, okay, and I know where the dose plane is for this particular dose delivery. So this is a patient plan that was exported and placed on this phantom, and then what I did was I exported the dose plane. The dose plane itself comes DICOM registered, so the 000 of this dose plane is basically wherever the crosshairs or the isocenter was set up at. So that's one important thing, is you need to know how to register the calculated data to the measure. In this case, the registration was the crosshairs in between the treatment planning system and the actual film, as you will see. I did my calibration curves, and this is the way that I did my calibration curves, usually 7 to 10 strips. You want to make sure your dose levels or your max dose levels are past the max dose level that you're going to be measuring at. I scanned each of those films. I put dose levels on each of those films. These dose levels were based on calculated values that I got from the treatment planning system to generate my cal curve. Your cal curve will go, of course, you choose one box, and with one box of film, you will do you first will do one cal curve, and then that cal curve is applicable. This is what it's called the, sorry, I forgot to mention that, the one scan protocols. And this is why I like this, is because this one cal curve, it's going to be applicable for all the films on that box, for all the films on that box, and you only have to do it once, okay? And once that cal curve is done, which is represented here, this cal curve here basically applies to any measurements made with films on that box. And after I'm done with this cal curve, I can take my actual film, put it in the measuring conditions, make my registration marks. But with this one scan protocol, the beauty of it is that you got your registration marks to align to the crosshairs that we talked about. But you also scan 2 or 3 pieces of film on that same day. The cal curve can be generated on one day, but then on the day of measurement, you can scan, you do your patient-related film, which is this one here, and then you scan other films with different dose levels, and then the software, in this particular software, uses this data here to sort of renormalize that previous cal curve. So you don't have to wait 2, 3, or however any hours for stabilization of the film. So within, say, an hour, instead of 24 hours wait period, within an hour, you should be able to read this data and make your intercomparisons. So you want to make sure you make your measurements, register your film. When you scan the film, you want to make sure your registration marks are good. And this is super important, especially if you're looking for 2 millimeters registration. It's important because then you're going to have questions about it. Your film measurement registered. So again, registration. And then the software does its comparison. And this was my SBRT comparisons at the 2%, 2 millimeters, and 98%, 98 to 99% agreement. And that's it.
That was great.
Sorry, I went so fast.
No, we took you over time, and maybe I'll just ask one final question unless somebody else has a question. But in the calibration curve, I really like it showed red, green, and blue channel calibration curves there, and the difference between them. Do you know if the software uses all three, or if it prefers just one?
No, the software, you can pick and choose, and it's got different equations for that cal curve. The equations that I use is a standard equation that the company recommends. Mostly for high doses, they recommend if you're, it's what is called multi-channel dosimetry. So you can use all channels, or you can use the red channel. And I can't remember now. They specify which channel is best for which dose level. And what I remember is that the red channel kind of gives me the best agreement. But there are papers published by Micah, and actually I sent you all those papers too, and these one scan protocol papers are in there in the stuff that I gave you. Sorry,
I really like the slide that's showing the 3 different channel calibration curves.
Yes, it does so. And the software itself, that's why I liked it. I mean, the company developed the film, and the company gave you the tools to be able to read this as best as we can possibly read it, you know. And I think that they put good mathematics and good science behind it. I do have to say that it's a quirky software, botanology wise, you know, trying to figure it out. But I think it does the job pretty good in terms of. See here, you have this equation here.
Yep.
So they have 4 different equations to model what the curve should look like. You know, to get the best fit so that you can get the best resolution in your steps. So I think that it's good. And this button here, you can either use the red button, the blue, for depending on which channel, and it will give you % differences on each one. And I do remember that the red one is the one I think I stuck with. It seemed to be for the SBRT cases that I looked at and the high dose region, that was the first best one.
So when you're measuring data for the TPS, you know, you're using the water tank and you're scanning and you're using film. We had a question from your previous presentation when you were validating the model. Do you think film is essential to that process?
I think film is essential to the process for answering discrepancies. If you, for example, in output factors, I think that they finally, I wasn't doing it. It was the SBRT chief. They did the diode, they did the film, they did the, back then they didn't have the micro chamber. Back then they didn't have the diamond chamber, because I remember buying the diamond chamber because I wanted to do small field dosimetry. Back then they had I think that they had the CC04 and or a bigger chamber. I can't remember what it was. So they did film measurements, and they combined the measured film data with the ion chamber data to kind of get their sort of finalized output factor. So in order to be able to resolve it, and that's what the other guys, when they did it, was you know, you can confirm in the end with film.
Got it.
But again, film dosimetry in itself, not done right, can introduce its own uncertainty. So it can be used to ascertain and establish the validity of the other detector data, and that's what I would use it. Like, if I have issues with a scanning curve that I've scanned, do a film on a single plane, export it out, and see what the ion chamber or what the detector looks like.
Yeah,
That's where I would. That's where I would bring in the film.
That makes a lot of sense. And
Yeah.
you know, in the validation part, you used EPID dosimetry a lot, and the assumption there is that it's already been calibrated and it's
Correct.
reliable. So like you're saying, if your tool, like a multi-detector or an EPID, is calibrated properly, that would be okay for validation. But if you
Yes.
see a discrepancy, then you would go back to film to verify
Yes.
if it's a calibration issue
Yeah.
or a measurement issue.
Yeah.
That makes sense.
Yeah.
All right. I don't want to take up any more of your time. You've invested 2.5 hours, and it's been a great session.
Okay.
I want to thank you for the presentation. Thank you very much. And thank you to all of our attendees. The session's recorded, and all of the files will be available through Rayos Contra Cancer. So reach out to them if you have any issues getting the DICOM fields and presentations, because it's all available for you guys.
Yeah.
Awesome.
The only one that is not exported is the chair. And to be honest with you, it's because I finally found that we have so many ARIA patients and so many files somewhere. So I was able to locate it, and I think I'm going to export that a little bit later on. But that chair file is actually the one that's being used now with the EPID to kind of tweak the parameters in the treatment planning system for DLGs and transmissions.
Yeah, it's a good test.
Yeah,
Awesome.
and if we can bunch up the machine, we separate the machine. You know what I'm saying? There's so many things you can tweak.
Yeah.
All right, guys.
Thank
Have
you.
a nice one wherever you guys are at, and hope to see you later on in other lectures.
That's great. Okay. Bye.
All right.
All right. Thank you.
Bye-bye.
Bye-bye.